Hello and welcome to today's session. We are in the GCSE PE Portal today, lesson 16, which is from the Anatomy and Physiology section from paper 1, and we're going to look specifically today at EPOC, or excess post-exercise oxygen consumption. Of course, if you haven't already, you can find the slides and the questions and the flashcards to go alongside this video at gccpeportal.com, or just head over to thepetutor.com. But we're going to get straight into the objectives today. Pretty simple ones. We are going to know the terms oxygen debt and EPOC. We should also know why EPOC occurs. And then at the end, we are going to go into some reasons behind EPOC occurring and what we can do to limit the negative side effects that it could pose, or what we could do to actually improve the utility of EPOC. So how can we actually promote it so that we can recover faster from exercise? It should run for about 15 to 20 minutes today. It's going to be quite a short lesson, but we're going to get straight into with a bit of a starter. And all I want you to do is think about a recent time that you ran, you cycled, you lifted weights, played sports, swam, did a triathlon, whatever you've done recently where you were active, and not just a walk, but a little bit more moderate. So from jogging upwards. So think of a recent time that you've been active, and after finishing, how did your body feel? What did you do post-exercise? So a few things to consider. How did your skin feel? How was your breathing? How was your heart beating? What was your temperature? Have a little think. Because our body, it goes through changes. Because as soon as we go from a resting state, like you most likely are now, either sitting or standing quietly and not moving very much, but that's a state of rest where there's no demand being placed on your body. As soon as you go into a state of movement or a state of exercise, changes have to occur in your body because you're demanding them to happen, because you're demanding additional energy release, you're demanding additional oxygen supply, CO2 removal. There's more muscular contractions going on. There's higher rates of cellular metabolism, breaking down the food that you've eaten into the kinetic energy that we need to move. And all of this creates change inside of our body. It knocks us out of something called homeostasis. So homeostasis is your resting level. It's your bog standard level of inertia, let's call it. It's your even ground, like you are probably in now. If you go into a really cold environment, you end up shivering. That's in an attempt for your body to get back to its normal even ground. If it's too hot outside, you start to sweat in a bid to cool down to get you back into a state of homeostasis. The same can be said with exercise. Resting is our normal state. As soon as we start to move more, we are out of state. We are in an increased state. So our body has to do something in order to reverse that almost, to get us back down from this heightened level back to our resting normal level. So have a think. How did your skin feel? Did it feel hotter? How were you breathing? Were you breathing faster or deeper? What was your heart doing? Could you feel it thumping in your chest? And what was your temperature? Were you starting to get warmer and warmer? Well, EPOC is likely linked to all of those things that you've experienced. So to start with, the definition. What does EPOC stand for? It's this here. Excess post-exercise oxygen consumption. So we'll just break those four parts down. Excess, we have got extra than normal, more than normal volumes of air coming into our body from which we can extract abnormal amounts of oxygen from it. So air and oxygen, not the same thing. We breathe lots of air in as we respire, but by doing that, we can extract increasing quantities of oxygen from that gaseous cocktail that air is. Post-exercise, so we're talking about the time period from finishing movement. From this picture here, you can see from finishing a race, but it doesn't end there. We continue to breathe a little bit heavier from the moment we cross the finish line, possibly a minute later, possibly 5 minutes later, maybe 10 minutes later. It depends on how hard the person was running and how tired they felt and how damaged their body was. O, oxygen. Like I just said there, we're not dealing with air here. Yes, we will see increased levels of air ventilating in and out of our body, but it's the oxygen we are most concerned with. Because we can breathe in lots of air, but not have the facilities inside our body, alveoli, capillaries, blood, to actually take the oxygen out of the air and deliver it around the body, and then take it out of the blood and use it inside the muscles and cells. Now, this is actually where we start to talk about the term VO2 max, the maximum volume of oxygen that we can actually take in and utilize around the body. Not just breathe in to then breathe it out again, but to breathe in, extract, transport, extract again, and then put to use. So it's the extra amount that we consume post-exercise of oxygen, not air, and then consumption. Another word for utilize. So not just get into our body, but actually transport around our body and put to work. So if you're looking for a definition that you're hoping to write down, then perhaps this could be it. EPOC is the extra quantity of oxygen that continues to be inhaled and distributed around the body after the termination of an extra session, or exercise session, I should say. So it's the extra amount. So right now, we are sitting or standing or resting, and we are breathing in air and extracting oxygen and utilizing it around the body. That's our normal level, our homeostatic level. The difference between where we are at the moment and what we experience post-exercise, that volume, that gap, that difference is the EPOC. That's the volume of EPOC, the volume of excessive post-exercise oxygen consumption. Now, our body's cardiorespiratory system remains in this elevated state after exercise to enable this to happen. Because, and we'll go into the reasons why we need the oxygen in a moment, but our heart keeps on pumping, hopefully, like you noted earlier in the starter. We keep on breathing faster and deeper. Our tidal volume remains larger. Our breathing rate remains more frequent. The same inside of our heart, which what I'll put here. How do we achieve this increased or elevated cardiorespiratory response? We have our minute ventilation and we have our cardiac output. These two formulas that we refer to within anatomy and physiology. Minute ventilation being the sum of breathing rate multiplied by tidal volume, and cardiac output being the sum of heart rate multiplied by stroke volume. How much air do we breathe in and out per minute? How much blood do we eject from the heart per minute? If we can keep these elevated, then we stand a better chance of extracting the oxygen, delivering it around the body, and utilizing it in our bodily cells. And if we can do that, then we know that EPOC is serving us. It's serving a purpose inside the body. So you might be thinking, what's the purpose and why do we do this? So it's because of this phrase here, oxygen debt. We are repaying the oxygen which we could have done with at the start of exercise, but we didn't have it there. So it's repaying this oxygen debt that was there at the beginning of exercise. Now, when exercise commences, there's not enough oxygen in the muscles to allow aerobic respiration to supply the energy. Now, hopefully you know from previous lessons that aerobic energy systems are more efficient in how much energy they can release from food, gram for gram, compared to anaerobic energy systems. Anaerobic energy can do it faster, but aerobic energy can do it more efficiently. Larger quantities from smaller supply, it just takes a little bit longer to do so, and we haven't got it so instantaneous. So at the beginning of exercise, let's say we go from our seated positions now, and we suddenly get up and start doing star jumps for 5 minutes straight. No rest, no breaks, just 5 minutes of star jumps. Eventually, perhaps around the 2 to 3 minute mark, our aerobic energy systems might kick in enough to supply the energy to fuel the muscles so that we can carry on the star jumps. But what about the first 30 seconds, minute and a half, 2 minutes? If we weren't using the aerobic system predominantly, we must have been using the anaerobic energy systems. And we know that anaerobic energy systems are not the most, I'm going to use the word clean, but by that I mean it's lactic acid producing. With aerobic, obviously we have the carbon dioxide or the water byproducts, but they're not as hindering as the lactic acid is. So the anaerobic energy systems, it burns out quicker, you could say. So anaerobic respiration, we know, is occurring at the start of exercise, and it's producing lactic acid as that byproduct. We know that we have glucose. Enzymes act on that glucose inside of our cells. It releases energy to move our muscles so that they can contract. But lactic acid is the leftovers, and lactic acid makes our muscles feel heavy. It slows down the productivity of enzymes, and eventually we just have to stop. It's that heavy feeling that you have in your legs, that burning sensation that you might have in your muscles when you're working too hard for too long. That's lactic acid, and we don't want it for high quality performance, we could say. But lactic acid can be broken down with additional supplies of oxygen. So where we have lactic acid being produced in the body at the start of exercise because we have to use anaerobic exercise, if we get to a point during exercise where there is some surplus, we might be able to start to chip away at the lactic acid that we did produce. But if, in that star jump example, we were only moving for 5 minutes, we probably wouldn't have got that chance. Especially if we were doing high intensity training where there's definitely no surplus oxygen. We've just got the lactic acid there sitting in our bodies, in our muscle. We just about move into aerobic energy systems and we're just about staying afloat. We're just about matching energy demands with our aerobic system, but the lactic acid remains in our body until the end of exercise. We stop moving, but we keep on breathing. Our heart keeps on beating at the same or similar levels as to when we were exercising. We keep consuming large quantities of air that we don't technically need for the exercise itself. We consume the air, we extract the oxygen, we transport it in the vascular network so that we can start to break down the lactic acid that we produced at the start of exercise. We built up this debt. We required oxygen at the start, but we didn't have it. So we wait until the end of exercise to repay that oxygen debt. That's one cause of EPOC. So here's how it might look on a graph. So in this blue section here, this is the deficit which creates the debt that we end up repaying. Now in this blue section here, you can see this void whereby our VO2 work, this sort of curving up yellow segment, we could call it. We've got this void whereby exercise is requiring demands at the level 40. But we haven't got it because we're still at resting levels. And hopefully, you know by now that when we start to exercise, there's a lag time between starting to move, our brain understanding that we are moving, understanding that there are increasing demands, and then sending its own messages to the heart and the lungs and the respiratory muscles to do something about it. There's a lag, and we can see that this lag plays out over 1, 2, 3, 4, 5, 6 minutes in this case. It's only around that 2 to 3 minute mark, which we referred to earlier, that 2 to 3 minute mark where it starts to flatten off. It's not accelerating as rapidly as it had to at the start. It's beginning to play a role in energy release because it's not like a light switch. We don't just switch from anaerobic energy systems, bang, aerobic energy systems. It's more of a merger. So it's almost like a sliding scale or a seesaw. We gradually tip from using one, then we go into the other. At some points, we might be using 50-50. But at the start of exercise here, we go from our homeostatic cardiorespiratory rates, very low, not satisfying the brand new oxygen demands presented by exercise. So we have this deficit, we have this gap, we haven't got enough oxygen inside of us. So I'm looking at this middle point here. At this point, our body's relying on the anaerobic systems, therefore producing lactic acid. The less intense this exercise is, obviously, the less lactic acid is going to be produced. If we don't need to produce as much energy as quickly, then we're not going to be using as much fuel, converting it to release the energy and producing lactic acid as a byproduct. So the less intense, the lower the lactate accumulation, the lower the lactate buildup. The lower the intensity, well, we're going to hit the oxygen demands sooner. So the deficit is going to shrink. It's going to be much smaller. But if we work at our maximum capacity, for example, a 400-meter runner, working at 90 to 100% of their maximum speed from the word go all the way around the track until they cross the finish line. It's going to take the maximum amount of time possible for the cardiorespiratory system to catch up, all the while they're producing lactic acid at the maximal rate as well. That's a huge deficit. So their EPOC is going to have to also be big to pay off that debt. Now, that's not the only cause of EPOC, but it's the primary one, especially in this fast stage, this early stage of repayment. Now, you don't need to know too much about the two stages at this point at GCSE. Moving into A-level, you'll look more closely at the fast stage and the slow stage of EPOC. You should be most concerned about the fast stage, which is the first couple of minutes, the first sort of 2 to 3 to 4 to 10 minutes of post-exercise. That's where you see that dramatic decrease, like you can see in this the green side of the graph here, this dramatic drop-off of oxygen consumption. Heart rate would come crashing down, respiratory rate crashing down, and then it gradually levels off, and that's when you would move into the slow stage, which we're not too concerned about at this point. So this green segment here is largely in place to pay off the deficit which we had at the start, so we're repaying our oxygen debts. So the oxygen debt is bigger than the deficit, however, because excess oxygen is required for the total repair and recovery. That's what I was saying there about the slow stage. And we need to take in oxygen to continue to release energy inside of the body to put our muscles back together, to make sure that we can fuel the muscles which are allowing an elevated respiratory rate. We need to make sure that we can supply energy for the replenishment of damaged blood cells, of damaged tissue cells. So it goes beyond lactic acid, but that's the primary cause of the first early stage of EPOC. We continue to consume it to repay what we needed at the start, but we didn't have it. So we produced lactic acid, so now we need to get rid of lactic acid. So how do we get there? Well, I've obviously already said the elevation of the cardiorespiratory system, but how do we achieve those? We'll look at minute ventilation first of all. So first, minute ventilation is the volume of air that enters the lungs each minute. If it enters, it also exits. Okay, so it's the volume of air that enters the lungs each minute. It's the grand total of opportunity that we have to extract oxygen. It's only from that body of air that we can pull oxygen out from. So how can we increase that figure? First of all, breathing rate, like we said at the start. Breathing rate is obviously going to stay high. The frequency of ins and outs, of inspirations and expirations. So our respiratory muscles, our diaphragm, our intercostals, our sternocleidomastoids, our scalenes, our obliques, our pectoral minors, these are all going to continue contracting to make sure breathing rate remains elevated, to make sure that tidal volume remains large, so that we continue expanding to bigger distances to fill our lungs to a greater depth. So we've got respiratory muscles working. That's going to require energy. How do we get energy? By inhaling and utilizing oxygen to allow aerobic systems to break down the food to release energy for contracting muscles. So we've almost got this self-fulfilling prophecy now of we need to carry on breathing harder and more frequently. In order to do that, we need to breathe in some extra oxygen to supply the energy to the muscles which are causing the more frequent and deeper breathing. But it's just a slither of the cause, or the slither of the quantity in EPOC. It's just a small thing now. But if more air enters the lungs each minute, then obviously more oxygen will be able to enter the blood and then get transported around the body. Second, we have the elevated cardiac output, or Q, as it's also written in the formula. But like we know, this is the volume of blood that is ejected by the heart each minute. How do we achieve that? We keep heart rate high. Now, maximum heart rate is roughly estimated to be 220 minus a person's age. Obviously, genetics and level of training and fitness and health and lifestyle can impact that, but roughly speaking, 220 minus a person's age. So the heart rate isn't going to remain at that level for very long at all, if it was ever near that in the beginning. We see that dramatic drop off, but it's going to stay significantly higher than resting heart rate for the foreseeable future, for the first 1 to 10 minutes, let's say, depending on the intensity of the work, depending on the duration of the work, depending on how damaged the body was, depending on the volume of lactate accumulation. There's a whole number of factors that can determine the exact volume of EPOC required, but we know it's going to remain elevated. Stroke volume is the volume of blood ejected per contraction from the left ventricle. So the left quadrant attached to the aorta, which ejects blood and transports it around the body. We want to see a slightly higher stroke volume so we can combine the two. A slightly faster heart rate than rest, perhaps 90 to 100 beats per minute, and a slightly higher volume of blood being ejected each beat. If we can achieve those two things, then we can keep our cardiac output higher than our resting levels, so that more blood can be circulated per minute, and hopefully in that blood we've got more oxygen because of our respiratory system extracting it in the alveoli, diffusing it into the capillaries, and then passing it to the heart to distribute through the vascular network. So that's a lot of information about what it is, what might cause it, the deficit, the debt, and how our body responds to paying off that debt: cardiac output, respiratory system. So now, what can an athlete, or you or I, do to support this necessary EPOC? What can we do to speed up the debt repayment of oxygen? Well, we've got a cool down. We need to have finished the exercise with some form of low intensity to moderate intensity movement. It doesn't need to be similar to the sporting actions. It doesn't need to be anything complicated. It just needs to be some form of strain on the body above resting levels. Why? Because this will help tell the brain that there's still some movement happening. We need to keep the heart rate, or we need to keep the cardiac output elevated. We need to keep the minute ventilation elevated. We're just helping the body identify to the brain that we need things elevated. So they're going to keep the heart rate, or the brain's going to keep the heart rate and the breathing rate high to satisfy the movements, but the movement's such a low intensity that we're creating this oxygen surplus that can go in to breaking down that lactic acid. Static stretching can also assist muscle recovery and prevent soreness the next day. Why? Because it can help our brains regain control of the muscle. If it was experiencing any form of cramping or stiffness or tightness, by stretching and holding it, it can start to minimize or switch off the neural control that the brain has over a muscle. So we can calm the muscle down, we can take the tension out of it, we can switch it off, then we can elongate it. So we can move sort of damaged and torn fibers back into its original place. You almost think of it a bit like foil sometimes, how if you press on foil from different directions, you can start to crumple it. A stretch, it's us putting it back on the surface and flattening it out so that it can be used again better next time. Also, we can prolong this cool down period. So we don't just want to do it for a few minutes, but if we can do it for an extended period of time, so say 5 to 10 minutes, then we know for certain that we're going to achieve that oxygen surplus on top of the movement demands to carry on paying off that lactic acid debt. If we can do that, then obviously the side effects of movement, where we have the increased temperature, we have the increased exhalation of carbon dioxide, then we know that we're going to keep on shunting blood to where the body needs. We're going to shunt blood to where the blood needs to go. So if we keep on moving the muscles which we've just worked, let's say a sprinter goes for a walk, those legs are going to be provided more oxygenated blood because the vessels will be dilated. They're going to be warmer. So more blood's going to be funneled in that direction. If we just stopped, then the temperature will cool down. The blood vessels will begin to constrict. The blood won't be able to get to those muscles in the same quantities. And if we haven't got the same quantities, or if we haven't got increased quantities of blood reaching the muscles, then there's going to be no opportunity for the extraction of oxygen into that muscle. So by moving, we tell our brain that we still need to keep our cardiorespiratory system elevated. By moving a muscle, we keep the vessels supplying it dilated. And by stretching, we can start to straighten out some of these fibers. We can start to gain neural control of the muscle once again. We can reduce the tension, and by stretching them and activating them, that's also going to require or demand oxygen supply or the blood supply, and helping with the dilation of vessels there as well. So, what are 4 things that we can do post cool down to promote recovery? So this is into the evening, the next day after that, depending on the intensity and duration of the work completed. So the first one is rehydration. Very important, not just to drink tap water, but also perhaps an electrolyte drink, depending on the intensity and the duration. Because when we exercise, lots of fluids are lost, lots of nutrients are also lost. And these nutrients are so important in the chemical reactions that occur inside of our muscles, which enable them to contract. So, in order to actually support our body's repair and replenishment, we need to consume fresh nutrients, be it micro or macro, so that we've got the relevant building blocks to put it back together, to complete the equations that can fuel the repair process, and we can continue to release energy. Second, we have diet manipulation. So glucose, looking at the top one here, glucose would have been converted into energy for movement. Therefore, carbohydrates should be consumed in greater quantities. So here we're talking more about the macronutrients. If we've moved a lot, then we would have expended we would have drawn from our glucose supplies. So we've moved more, we've consumed our energy stores. If we want to move again in the future, then we need to replenish the energy stores. So the diet should be consuming a carbohydrate-rich option. We also need to be consuming protein, because within the protein, we have amino acids, which are the building blocks of the muscles and tissues and cells that we need to not only live and survive, but also to perform at our optimal levels. So we rehydrate to make sure that we've got adequate water content inside of our body, and we've got electrolyte content and micronutrients and minerals inside of our body. We then need to manipulate our diet, so we've got adequate carbohydrates and proteins and fats coming back in, which we might have expended. And we could also massage. Now, massage is an option to stimulate blood flow in an area which might still be sore. So by prodding and poking and massaging and manipulating a muscle, that's going to tell the brain that something's happening. Therefore, blood is going to be sent and it's going to stimulate that increased blood supply, therefore increased oxygen extraction, therefore energy is going to be released into that muscle better so that we can start to repair it sooner. Lastly, we have ice baths. Now, this one is up for debate, or cold therapy in general. There is theory that backs it up, but there are also scientific findings that might refute some of the claimed benefits. But we'll leave it in for now. But ice baths, or exposure to any sort of cold. The theory goes that immediate or sustained exposure to cold can cause blood vessels to constrict. And by doing so, apply pressure to the blood inside to squash it and squeeze it back towards the heart. And then when you exit the cold environment, they dilate back to normal levels. So we've gone from a shrunken blood vessel, which has squeezed out old blood, damaged blood cells, lactic acid that might have accumulated. It squeezed it out, and then as it opens back up to normal levels, a whole batch of fresh blood, freshly oxygenated blood, can come to that muscle site, And oxygen can jump out, go into the muscle, and fuel those recovery processes. But, like I said, scientific research has come out to refute it, but the theory goes constriction can get rid of old blood, and then as it dilates, there's room for new blood with new and larger supplies of oxygen to better fuel the recovery process. So 4 main recovery methods that you need to know: rehydration, diet manipulation, massage, ice baths. And that is that. So there is an activity if you are using the GCSE portal. So you can go ahead and use these slides or this video to give that a go yourself. But hopefully now you do know the following things: oxygen debt. What is it, and where can you see it on the graph? 3 methods to better recover from vigorous exercise. And you should also understand why EPOC occurs. It's that lactic acid accumulation at the start because we rely on anaerobic energy because aerobic systems haven't had a chance to catch up yet. And hopefully you'll be able to evaluate those recovery methods that we just covered there. So with the rehydration, what are some pitfalls or some drawbacks to rehydrating early or late? And then maybe the ice baths, there is some scientific research saying that it isn't impactful. It could bring on cramping, but there are some benefits in theory to it as well. So that is EPOC, excess post-exercise oxygen consumption. I hope you found that lesson useful. If you did, then visit the PE Tutor or the GCSE PE Portal, and you can find out more about this video, the lesson slides, the flashcards, the activity sheets, and the quiz questions that we have going on over there. I'll see you again in the next one. Bye for now.